This is all about Euler's formula, and the purpose of Euler's formula from a really practical viewpoint in this course is that it helps you manage complex numbers as exponents. Okay, so for a real number x, e to the ix equals cosine x plus I sine x. And there's various ways of proving it. I think the most straightforward way to see it is using Taylor series. We're not going to do it here. But it helps you go from polar to rectangular. So, if you see 3e to the I pi over 3, that's 3 times cosine of pi over 3 plus I sine pi over 3. And you can, simplify from there to get 3 halves plus I 3 root 3 over 2. Now, for a complex number, x plus iy, if it's in the exponential, you break it up and you use Euler's formula. So e to the x plus iy is e to the x times e to the iy, and then we're going to say that's e to the x times, and apply Euler's formula to this part, cos y plus I sine y. So e to the 2 plus I, or 2 plus I times 1, is e squared times cosine 1 plus I sine of 1. More generally, for a complex number, e to the iz is cosine z plus I sine of z. And you can notice a few things from applying that formula. Cosine of z is 1/2 e to the iz plus e to the minus iz. It's a way of canceling out the terms with the I in it. And sine of z is 1 over 2i, e to the iz minus e to the minus iz. If you want to see this, it's not hard. Let's take the cosine expression here. We calculate e to the iz is cos z plus I sine z. E to the minus iz is cos minus z plus I sine minus z. Since cosine is since cosine is an even function, we can lose the minus sign inside the cosine. So e to the minus iz is actually equal to cosine z. And since sine is an odd function, that minus comes out here, and it's minus I sine z. So when we add these two quantities together, the I terms cancel out. One is a plus, one is a minus, and we're left with 2 cosine z. And then if we divide by 2 on each side, we get the identity we were trying to show. And a great thing is that if you understand how to use Euler's formula, you really never have to remember trig identities. I can never remember them. So let's find an identity for sine of 2z. All right. Step 1, use kind of the definition of sine. We know we can write it as e to the 2iz minus e to the minus 2iz over 2i from what we just wrote on the previous page. And then I'm going to use rules of exponentials. E to the 2iz is the same as e to the iz squared. And e to the minus 2iz is e to the minus iz squared. So inside each of these sets of parentheses, I'm going to apply Euler's formula. E to the iz squared becomes cos z plus I sine z squared. E to the minus iz squared becomes cos z minus I sine z squared. We have a minus sign connecting them, and we have divided by 2i in the bottom. And then it's just algebra, right? We expand each of the squares, right, using rules for squaring things. We get cosine squared z plus 2i cos z sine z minus sine squared z from squaring this I up here. Then we have minus cosine squared z plus 2i cos z sine z plus sine squared z. These cosines cancel out. These sine squareds cancel out, and we get 2i cos z sine z here, plus 2i cos z sine z here, all over 2i. That's 4i cos z sine z over 2i, or 2 cos z sine z, right? Easy way of deriving lots of trig identities. All right, thanks for listening.